Welcome back to the deep dive. Imagine a world. Okay, what if scorching deserts could actively cool down bustling cities and Arctic chills? What if they could warm homes thousands of miles away? Think about our biggest climate challenge, this massive waste of thermal energy. What if that became our greatest resource? Today, we're diving deep, not just into an idea, but exploring a potential blueprint for, well, a planetary circulatory system. It's a monumental concept, really, that could genuinely redefine our very relationship with heat and cold.
That's exactly it. The core challenge we're facing is that thermal energy is it's constantly exchanged and lost all around us. And there aren't any robust large-scale systems to reclaim it or redistribute it effectively. Think about all the waste heat from power plants, industry, or the energy we pour into air conditioning that just vanishes.
Yeah, gone.
Exactly. It leads to immense global waste. It makes our climate challenges worse. And frankly, it creates huge disparities.
Yeah.
Access to comfortable temperatures isn't equal around the globe. So our mission here in this deep dive is to explore this conceptual infrastructure. Something like the global electrical grid, maybe, but entirely dedicated to intelligently managing heat and cold. It's an idea that, look, if it could be realized, it could profoundly impact our existence. It could create a new kind of planetary harmony.
That's a powerful vision. Okay, so let's get into the nuts and bolts then.
Yeah.
Where do we even begin? How do you build something like this?
Yeah.
What's the foundational tech? You mentioned this Global Thermal Vacuum Conduit, the GTVC. What exactly is that? What makes it so different from, say, just a really insulated pipe?
Well, the GTVC, it really is the technological artery of this whole system concept. And what's fascinating, truly ingenious really, is its multi-layered structure. That's absolutely key to its promise of near-zero thermal loss. Imagine it like a super-armored, vacuum-sealed pipeline. The outermost layer, it's an incredibly strong, smart alloy composite.
Like what?
Picture something like graphene-infused titanium, something that gives it the structural strength to handle anything desert sun, Arctic blizzards, you name it.
Okay, tough stuff. Built to last. What's inside that?
Right inside that shell, you have what's called the vacuum gap. It's a near-perfect vacuum space. And this is crucial because it basically eliminates conductive and convective heat transfer. Stops heat or cold leaking through the walls.
Right, like a giant thermos bottle kind of idea.
Exactly, yeah. A super efficient thermos, but on a massive scale. Then, inside that, there's a radiation shield. It's typically an aerogel-based reflector lining designed specifically to block thermal radiation, stop solar interference messing things up.
Okay.
The actual work, the transport, happens in the phase change channel. This uses a specialized liquid mixture, a slurry of phase change materials, PCMs, or maybe a super efficient nanofluid.
That's where the heat or cold actually travels.
Precisely. And finally, running right through the middle, like a spine, is the sensor spine. It's equipped with quantum dot thermal sensors. These give real-time monitoring, allow for intelligent AI routing.
So the system knows exactly what's where, temperature-wise, and where it needs to go. That's a remarkable piece of engineering. So if this multi-layered conduit is the artery, what's the blood? You mentioned these PCMs. Are we talking about, like, highly specialized liquids that basically soak up heat or cold as they change state? Sort of like how ice melts in a cooler. Right. But way more efficient. How does that connect to this idea of transferring temperature, not just energy? That sounds important.
Precisely. That distinction is huge. For heat, yeah, we're talking about materials like molten salt microcapsules or perhaps graphene-enhanced glycols. They're chosen because they absorb and release huge amounts of latent heat when they change phase. For cold, the concept leans more towards liquid nitrogen hybrids or maybe cryostable hydrofluorocarbon blends. These materials do a similar thing, but at extremely low temperatures, absorbing and releasing cold when they change state, say, liquid to gas. And that transferring temperature, not just energy insight, it's fundamental. It means we stop thinking of heat or cold as just waste. We're not trying to convert thermal energy into electricity, send it somewhere, then convert it back, losing efficiency at every step. No. Instead, we're physically moving the thermal state itself, turning a byproduct into a portable, on-demand commodity.
Wow, okay. That's a different way of thinking.
Right. And there's even the idea of a neutral conductor, like a nanocarbon slurry, maybe, for just balancing things out, acting as a thermal buffer when needed.
That distinction really does change the game. But how would a system this massive actually work globally? How do you push heat from, I don't know, the Sahara to Siberia without using more energy than you're moving?
That brings us to its operational modes, which are pretty clever. It's designed for bidirectional flow, meaning thermal energy, heat or cold, can be routed dynamically. east to west, north to south, wherever it's needed, based on real-time global demand.
And something figures that out.
Yes, an advanced AI system, the concept calls it TempraNet. It would constantly forecast load distribution, analyze climate data, and intelligently redirect these thermal packets. And we also have what's called modular branching. Think of local pulse points, like sophisticated thermal substations. These can tap into the main conduit, the GTVC, for district-scale redistribution.
So cities or industrial parks could plug in.
Exactly. And these pulse points would have automatic gate valves. For rerouting flow, or even for emergency shutoff, say if there's seismic activity or maintenance needed, the advantages become pretty clear. Near zero thermal loss, really rapid routing because the PCM fluids are efficient, real-time AI optimization to balance demand globally, and built-in fail-safes with these modular shutoffs and alternative branches.
It sounds incredibly ambitious, almost sci-fi. What do you think is the single biggest engineering hurdle here, making the GTVC a reality? Is it the materials, the PCMs, the AI?
Yeah.
Something else?
That's a great question. Look, the material science for the alloys and PCMs is definitely cutting edge, no doubt, but arguably the biggest engineering challenge. Maintaining that near-perfect vacuum over potentially thousands and thousands of kilometers.
Huh, yeah.
Any leak, even a tiny one, compromises the insulation, the efficiency, everything. It demands, frankly, unprecedented levels of precision in manufacturing, installation, and especially in continuous real-time monitoring, detecting and sealing microscopic breaches almost instantly.
And that's where the sensors and AI come back in.
Absolutely indispensable. The quantum dot sensors, the AI analysis, they'd be constantly checking for any integrity issues.
It's incredible to think of just one GTVC, but the real vision here, it goes way beyond that, doesn't it? We're talking planetary scale. How does that even begin to look?
Right. So if we zoom out, connect this to the bigger picture, the vision expands to what's conceptually called the planetary thermal superconducting loop, the PTSL. And what's really insightful about the PTSL isn't just moving temperature around, it's how it treats the entire planet as a single massive thermal battery.
A planetary thermal battery. Wow. That's a powerful analogy.
Isn't it? It shifts the whole frame from localized energy problems to a global, interconnected thermal ecosystem. The idea is making every unit of heat or cold potentially reusable, endlessly circulated. So it's envisioned as this globally distributed, superinsulated, high-efficiency thermal loop, transporting and storing heat and cold using advanced PCMs, maybe cryogenic coils, huge subterranean heat banks.
So what are the main parts of this PTSL network?
Okay, core components would include the thermal conduits, that's the GTVC idea, but scaled up, forming the global backbone. Then you'd have regional energy walls. Think vast underground reservoirs, maybe old mines or purpose-built caverns, filled with dynamic PCM modules for long-term buffering.
So storing summer heat for winter use, potentially.
Zigzag, or storing deep winter cold. Holding energy for months. Then you need dynamic thermoswitches, AI-regulated valves, essentially for redirecting flow and balancing load across the whole network. And thermal exchanges. These are like the substations of the grid. Receiving thermal energy, modulating it, maybe boosting or lowering the temperature slightly, and dispatching it based on local demand.
Okay.
And here's something really crucial, maybe groundbreaking. Oceanic and geothermal nodes. These would be massive input-output systems designed to capture excess heat from volcanic or geothermal activity, basically tapping Earth's internal furnace. And conversely, using the deep ocean's immense cooling capacity as a huge, stable cold sink.
Harnessing the planet's own systems.
Precisely. And the emphasis throughout always is on nearly lossless transmission thanks to the vacuum tech or cryogenic systems and sophisticated AI predictive routing. To avoid bottlenecks, maximize efficiency.
So let's make this tangible. This system could literally move excess heat from, say, Sahara solar farms and pipe it directly to northern cities struggling with heating costs. Or take that deep-sea coldness and use it to cool equatorial zones facing unbearable heat stress.
That's the operational goal, yes. It ties directly into this idea called the Thermoverse Manifesto, which envisions this planetary circulatory system designed for thermal harmony, where theoretically a comfortably warm morning in Nairobi or a cool evening in Oslo could, to some extent, be engineered, supported by this grid.
But that phrase, engineering a morning, it sounds almost, well, hubristic, maybe too powerful. Yeah. What are the ethical lines here, or just the practical limits to that kind of planetary control?
That's a really critical point to raise. The engineering aspect, as envisioned, isn't about micromanaging every cloud or every degree Celsius everywhere. It's more about establishing a baseline thermal stability. reducing the devastating extremes and providing more equitable access to comfortable, livable temperatures. The system aims to mitigate the effects of climate volatility, not necessarily to override natural climate processes entirely. That would be, well, likely impossible and certainly unwise.
Okay, so it's about balancing, not controlling nature itself.
Exactly. There would definitely be limits, sheer scale, the energy required for massive interventions. The focus is intended to be measured, responsive, based on human need, ecological balance, empowering communities, not playing God with weather cycles.
That makes sense. So this Thermoverse global grid map, practically, what does it look like? What are the key points in this planetary thermal map?
Well, the vision outlines several core infrastructure rings. You'd have an equatorial heat loop, harnessing the intense solar heat from the tropics and helping direct that thermal flow globally. Complementing that, a polar cryonet, tapping the Arctic, Antarctic, and deep-sea cold zones as global chill banks. Then you'd have urban pulse points in major cities, smart cities, with AI managing local thermal meshes, distributing energy efficiently within the urban area. And beneath it all, potentially, these subterranean energy wells for that long-term heat and cold buffering we talked about.
Right.
And then specific regional nexus hubs would play specialized roles. Maybe the Sahara Nexus as a major soul flow hub, massive solar heat harvesting. The Andes Nexus could be a geothermal node plus a cryosync buffer balancing heat and cold inputs. Tokyo Pulse Point might be a test bed for advanced AI routing in a dense urban mesh. And the Arctic Core could act as a cryosync command center managing the planet's primary cold reserves.
I have to say, I'm really struck by the thought that went into the visual identity concept. You described it as interwoven rings of red, blue, silver, suggesting flow, balance, and the typography pitch, NASA meets Tesla. That's quite specific, futuristic, clean. It feels like this is positioned as more than just infrastructure. It's a global utility needing a public face. What's the thinking behind presenting it like that and these taglines like redesigning Earth's circulatory system or we don't just store heat, we store hope? Why that emphasis?
It's precisely because this is envisioned as more than just pipes and sensors. It aims to be a fundamental shift in how we interact with the planet's energy. The visual identity, the taglines, they're designed to convey the immense scale, yes, but also the elegance of the engineering and the profound potential impact humanitarian, environmental. Redesigning Earth's circulatory system that deliberately evokes something natural, vital, like blood flow, presenting the network as essential, life-sustaining for the planet.
Okay, I see that.
And we don't just store heat, we store hope. That speaks directly to the climate crisis, doesn't it? It frames thermal management not just as a technical fix, but as a pathway, a path towards a more stable, equitable, resilient future. It's about building public trust, maybe inspiring global cooperation, making it feel less like some cold utilitarian machine and more like a shared living solution.
That really does bring a different dimension to it. Okay, so beyond this top-tier PTSL, are there other maybe complementary systems, things that would work alongside it?
Oh, absolutely. The concept includes layers. The next best system, as it's sometimes termed, is the Hybrid Atmospheric Thermal Duct Network, the HATDN. Think of this as like, well, supercharged HVAC, but for entire regions, a semi-aerial ductwork system.
Like in the sky?
Sort of. It would leverage atmospheric pressure differences, passive cooling, passive heating. Components might include things like stratospheric intake towers reaching high up to capture cold air or vent waste heat vertically. You might have ground-level thermal reservoirs, maybe enhanced with thermal batteries for shorter-term storage. Using thermoreflective materials on city surfaces to bounce back unwanted heat, but also maybe capture usable warmth. And even seasonal thermofarms imagine large open areas using specialized materials to passively absorb and store the ambient temperature swings between seasons ready for later use.
And the advantage there?
Well, its strengths are potentially being less invasive than burying massive conduits everywhere, possibly easier to retrofit into existing urban areas, and it could offer a more rapid, localized response during, say, heat waves or sudden cold snaps.
Okay, and what about even smaller scale, like individual buildings, neighborhoods, factories? How do they plug in?
Right. That's where the supplementary system fits. Distributed Local Thermal Meshes, or DLTM, envision thousands of modular neighborhood-scale thermal energy nodes, basically like localized heat or cold batteries networked across cities and industrial areas. You could have thermal capacitor units inside individual buildings. These would allow buildings to share excess heat or cold directly with their neighbors via predictive AI, instead of just wasting it.
So my office building could send its waste heat to the apartments next door in winter.
That's the idea.
Yeah.
And in emergencies, you could even have mobile thermal shuttles trucks carrying temporary heat or chill storage moving between local nodes, like thermal ambulances almost.
Yeah.
It creates this really robust, redundant network from the ground up, complementing the big loops.
This is truly a colossal undertaking, thinking about all these layers. How would you even begin to deploy something this grand? Is there a phased strategy outlined?
Oh, definitely. Implementing something of this magnitude demands a very structured, phased approach. It couldn't happen overnight. Phase I, maybe the first 3 years, would likely focus on prototyping. Building and testing thermal routing loops in places with high temperature variance deserts, the Arctic, really stress testing the core GTVC tech.
Prove the concept first.
Exactly. Then phase 2, maybe years 3 to 8, would involve building the first core heat and cold exchange substations, those pulse points in major megacities and key industrial zones. Anchor points. Phase 3, say years 8 to 15, that's when you'd see the major expansion, extending the global conduits, building the regional energy wells, and rolling out the local thermal meshes more widely. And finally, phase 4, 15 years and beyond. That's when you get to the full AI-governed load balancing across all zones, using predictive climate modeling to really try and achieve that planetary thermal harmony.
That's an incredible roadmap. And underpinning all this, the vision mentions specific divisions or agencies, TempraNet, CorpPulse, CryoSync. It sounds almost like a new layer of global coordination or governance even. What's the thinking there?
Yeah, it's less about governance in a political sense and more about creating highly specialized entities for critical functions. You'd need that focus to manage something this unprecedented. So TempraNet would be the brain, right? Handling the predictive AI, the global demand forecasting. CorpPulse would be like the central nervous system managing the global routing, network integrity, keeping the flows moving. CryoSync would specialize entirely in cold energy managing storage, optimizing distribution from those polar and oceanic sources. SolFlow would spearhead heat harvesting from solar farms, geothermal zones, industrial waste. And PulseForge, that would be the dedicated R&D hub, constantly pushing innovation in materials, conduit design, thermal storage, AI algorithms, keeping the system evolving.
So specialized arms for a complex body.
Precisely. It ensures expertise, efficiency, and importantly, continuous improvement for the whole system.
It's quite something to contemplate. In a future where entropy, climate volatility, they increasingly challenge our survival, this conceptual construct really does offer a radical new path. What's the biggest takeaway you hope listeners get from this deep dive?
My hope, I think, is that it shifts our perspective on what constitutes waste and what constitutes imbalance. In a future where thermodynamic losses, entropy, relentlessly challenge us, this kind of conceptual framework, it could help invert those losses, turn them into tangible social gains. Look, a global thermal grid might feel like science fiction today, I get that. But then again, so did a global internet once. So did resilient AI not that long ago. This vision, it reminds us that we potentially have the ingenuity to redesign our fundamental relationship with energy.
It's where entropy meets intention.
Entropy meets intention. That's a powerful thought. So what stands out to you listening to this? Imagine the profound implications. A system like this for climate equity, for resilience. If temperature really could flow like power across our planet. Consider how this vision from its tiniest components to these vast planetary loops, how it could reshape our world, our relationship with thermal energy. What would it mean for your life, your city, your continent? If temperature became a resource we could truly manage, not just a force we endure, something to think about.